In this video, we're going to look at composition of functions and the difference quotient. When we think about the composite function, if we're given two functions, the composite function is taking one function and substituting it into another function. So given f of x equals the square root of 3x minus 1 and g of x equals x minus 5, we want to find f of g of x and its domain. Remember this function notation f of g of x is sometimes written like this, that f open circle g. So just different notations that you might have been exposed to. So first we want to just find f of g of x. So we're going to substitute g of x with x minus 5. And now f of x minus 5 means everywhere you see an x in our function f, we're going to plug in x minus 5. So this is the square root of 3 times x minus 5 minus 1. So looking at that f of x function, it was the square root of 3x minus 1, but instead of x, now we have x minus 5, which simplifies to the square root of 3x minus 15 minus 1, or the square root of 3x minus 16. So there's our composite function f of g of x. Now to find the domain, we're going to look at two different levels and find their intersection. First, you're going to look at the domain of the composite function. So our composite function was the square root of 3x minus 16. We know that for a square root function, the argument must be greater than or equal to 0. So our domain is going to be found by taking 3x minus 16 and setting it greater than or equal to 0. Adding 16 to both sides, 3x is greater than or equal to 16. X is greater than or equal to 16 over 3. And you're also going to look at the domain of the inside function. Our inside function was g of x, or x minus 5. That domain is all real numbers. So we're looking at two different sets, and the and means the intersection. So the intersection of values greater than or equal to 16 over 3 and all real numbers is in fact just all values greater than or equal to 16 over 3. Written as an interval, that's going to be 16 over 3 to positive infinity. So we've seen composite functions in previous classes. What we're going to look at that's new today is decomposition. And decomposition is a process that you're just trying to figure out what the two functions were that we put together initially. This is an important process, an important tool in calculus. You're going to learn about differentiation in calculus, and in particular, you're going to be learning about something called the chain rule. And in the chain rule, you are trying to take the derivative of some composite function. And in order to do that, you need to know what are your inside functions and outside functions. So what were the two functions that we put together? So obviously, we're not learning calculus now, but we are going to look at identifying your inside and outside functions for a composite function. In other words, we're going to decompose a composite function. So we're decomposing h of x, which is equal to f of g of x. So we're trying to figure out what is f of x and what is g of x. F of x is our outside function. Again, I'm basing that off of this definition of h of x equals f of x of g of x. So f of x is the outside function, and g of x is the inside function. Given h of x equals sine of 3x minus 6, our inside function is going to be g of x equals 3x minus 6. That's what's on the inside. And then our outside function is that sine. So it's going to be just sine of x. And you could quickly verify this by taking f of x and g of x that we just found and trying to figure out what f of g of x would look like. And you would arrive at this composite function h of x. We're also going to review the difference quotient. The difference quotient, you've seen it before in algebra courses. What this actually represents is the formula for the slope of a secant line through 2 points on any function. There's a lot of applications for the difference quotient in calculus. I'm not going to get into that in this video, but ultimately you're going to be using this to find slopes of lines in calculus. So the formula for the difference quotient, so we can call this dq, which is the slope of your secant line, is equal to f of x plus h minus f of x all over h. This is truly just an exercise on function notation. So finding the difference quotient of f of x equals 2x squared minus 3x plus 5. So in order to complete the formula for the difference quotient, we need to know what f of x plus h is. This is not just taking our function and adding h to the end. This notation means plug in x plus h everywhere you see an x in our function f. So f of x plus h is equal to 2 times x plus h squared minus 3 times x plus h plus 5. And now we're going to simplify this. The x plus h squared, I'm going to simplify that in a minute. First, I'm just going to write it out twice so I remember to FOIL. I'm going to distribute the -3, so we have minus 3x minus 3h, and then our plus 5 is still there. Now let's FOIL the x plus h squared. 2 times, this is going to be x squared plus 2hx plus h squared minus 3x minus 3h plus 5. Distribute the 2. 2x squared plus 4hx plus 2h squared minus 3x minus 3h plus 5. So there's our f of x plus h. And now we have all the pieces we need to plug into the formula for our difference quotient. The difference quotient, which is the slope of our secant line. And let me just quickly review a secant line. A secant line, if you think about a curved line, say a parabola, a secant line goes through that curve twice versus a tangent line, which only touches the graph once. And this is truly hinting at where you're going to go with the difference quotient in a calculus class. So we're going to be using that slope of the secant line to then use it to figure out what the slope of a tangent line would be. But that's something that you have to look forward to when you take calculus. So this difference quotient is going to be f of x plus h. I'm just going to copy that whole expression that I have right above. So 2x squared plus 4hx plus 2h squared minus 3x minus 3h plus 5. And now I'm going to subtract all of f of x. So I need to make sure I have parentheses around f of x. That was 2x squared minus 3x plus 5. And this is all being divided by h. Now we're going to use some more advanced simplifying here so that I can not rewrite this entire expression. I'm going to think about what happens if I distribute that minus sign without rewriting it. So if I distribute this minus sign to the 2x squared minus 3x plus 5, the end, I'm going to get 2x minus 2x squared, or 2x squared minus 2x squared. Those are going to simplify to 0. I also have a minus 3x from my f of x plus h, and now we have a plus 3x. So those are going to simplify to 0. We have a plus 5, and now we're going to have a -5, which sum to 0. So we're going to end up removing a lot of terms. Okay, looking across, we're left with 4hx plus 2h squared minus 3h, all divided by h. Since all of the terms in the numerator have a factor of h, that factor will simplify out. So this 1h, one of those h's, and this h will simplify with the h in the denominator. And we're left with 4x plus 2h minus 3. And that's our difference quotient for the function f of x equals 2x squared minus 3x plus 5. So very heavy algebra, but that's all it is. There's nothing extra fancy happening here. We're just using a bunch of function notation and simplifying using some basic algebraic rules. Find the difference quotient for the function g of x equals the square root of x minus 5. So I'm going to do the same thing. I'm going to start by identifying what is g of x plus h. Well, if I plug in x plus h where we see an x, this is the square root of x plus h minus 5. So our difference quotient, or the slope of our secant line, is given by the formula g of x plus h, or the square root of x plus h, minus 5 minus g of x. So that's in parentheses the square root of x minus 5, all divided by h. Now, thinking about simplifying, we're not going to be able to simplify anything with those radicals because they have different radicands, but that minus 5 and that plus 5 will simplify to 0. So then we have the square root of x plus h minus the square root of x over h. Now, to complete the difference quotient, we're actually going to rationalize the numerator. We want to ultimately get rid of h in the denominator. That's our goal when we're completing this difference quotient. So to get rid of that h in the denominator, we're going to rationalize the numerator by multiplying by the conjugate, sorry, forgot the word, the conjugate of the numerator. The conjugate of the numerator is going to be the square root of x plus h plus the square root of x. And we're going to do that to the top and the bottom. So the square root of x plus h plus the square root of x. In the numerator, we're going to have to FOIL. In the denominator, we will distribute. In the numerator where we're FOILing, because we're multiplying conjugates, when we FOIL, the outer and the inner terms are going to cancel out. They're going to sum to 0. So we really only have to multiply the first and the last here. The square root of x plus h times the square root of x plus h is x plus h. Minus, because it's a negative times a positive, the square root of x times the square root of x is x. Over, I'm going to leave this not distributed, so I'm going to leave it factored. The square root of x plus h, or h times the square root of x plus h plus the square root of x. Because if we notice in the numerator, those x's sum to 0. So we're left with h over h times the square root of x plus h plus the square root of x. And now those h's simplify to 1. Our difference quotient is 1 over the square root of x plus h plus the square root of x. We're just going to leave it like that. I know traditionally we don't like radicals in the denominator, but in this particular application, we're okay with it. All right, let's do one more. Find the difference quotient for f of x equals 1 over x. Again, starting with finding that f of x plus h, that's going to be 1 over x plus h. So our difference quotient, or the slope of the secant line, is going to be 1 over x plus h minus f of x, or 1 over x, all over h. Now we're just going to clean this up by identifying, basically we're just trying to get rid of this complex fraction. So if I know what the LCD is of all the fractions, which there's only fractions in the top, we're going to multiply the top and the bottom by that. So I'm going to multiply the numerator by x times x plus h, which is that LCD in the numerator. I'm also going to multiply the denominator by x over x plus, or x times x plus h. If I distribute this x times x plus h to both terms, and the first one, the x plus h is simplified to 0, so we just are left with x. And in the second term, the x is simplified to 1, so we're going to be left with minus x plus h. Make sure you've got those parentheses there because of the subtraction. And then we're going to be left with h times x plus h. Again, choosing not to distribute that. In the numerator, those x's sum to 0, and we're left with negative h over h times x plus h. And our h's will simplify, leaving just negative 1 in the numerator. So this difference quotient is negative 1 over x times x plus h.